testing of hypothesis, which is called the backbone of statistics, because we want to draw inference about the population based on the sample. And the entire crux of the statistics is revolving around this concept, which is called estimation and testing of hypothesis. So I will go through this concept as introduced by Dayashankar ji. I'll just give a brief introduction of myself, what I'm doing actually. Basically, I'm professor in the Department of Statistics, Punjab University, Chandigarh. And also, I was coordinator Center for Systems Biology and Bioinformatics. In fact, I established the Center for Systems Biology and Bioinformatics at Punjab University, Chandigarh. And I headed that department for 9 years. And my area of research is biostatistics. I'm working into the area of cancer modeling, then how to find out disease associated with a particular kind of disease. So this kind of work we are doing in collaboration with NIH, which is called National Institute of Health in US. So recently I came back from US after working with 2 centers. One was NIH, National Institute of Health. Another was VA Medical Center, which was in Dallas, Texas. And this NIH is in Bethesda, Washington, near to Washington, DC. And moreover, we are working on 6 other projects with WHO, ICMR, Indian Council of Medical Research, PGI, MER, and some other hospitals. So basically, we are working into the problems of biostatistics, particularly predictive modeling. So with this little bit of background, I'll move on to my topic, because I think 16, 17 participants are already joined. And we have to cover a very important topic of estimation and testing of hypothesis. So let me share the screen and then I'll start. Just give me 1 minute. I'm just sharing the screen. So hopefully you will be able to see this. Can you see my desktop? Is it possible now?
Yes.
Yeah. Okay. Thank you so much. Okay. Is this PPT is visible?
Yes, sir.
Yeah. All right.
Yes, sir.
Good. If somebody can just have a listen to me or respond, then I'll be sure that what I'm talking is you are receiving in a better way. So this is a national workshop on qualitative research methodology in social sciences. Although my area of research is biostatistics, but I have done a lot of papers in social sciences, also medical sciences, biological sciences, management sciences. So published around 100 and more than 140 research papers in different journals, and written several books also. One of the book which I have written on medical statistics is now, people are following that book, in which contains a lot of information about meta-analysis, mixed modeling, ANCOVA, MANOVA, all these things, ROC curve. So my topic is basically estimation and testing of hypothesis. So if you see this topic, there are 3 words. One is estimation, another is testing, and the third one is hypothesis. So I'll explain you the meaning of each and everything. Now, before doing or proceeding for this topic on estimation and testing of hypothesis, one should be very much aware of the nature and types of data. So I'll just maybe take 3-4 minutes to explain you the nature and types of data, so that you should not make any mistake in analysis of data, because many of the softwares, even I'll do some of the practicals today using SPSS, they will ask you, your data belongs to which kind of scale, and your data is of which type. Or so just bear with me for 5 minutes before coming to this topic of estimation and testing of hypothesis. All right. Look at the nature and types of data. If you look at the nature of data, it is basically of 2 types. Either it is called structured data or it is called unstructured data. Now, what do you mean by structured data? Structured data is the one where features can be easily extracted. For example, if I give you 100 observations, say related to height or weight, and I ask you to compute what is the minimum value, what is the maximum value, mean, median, mode, skewness, kurtosis, percentile, deciles. So all these things can be easily computed for numeric data. And most of the time, the structured data is in the numeric form. But what happens sometimes, the data may not be exactly in the numeric form. It could be in the form of labels, but easily convertible into numeric form. For example, gender. Now, gender is not numeric as such. It's simply a label, male and female. But I can always assign certain codes, say male as 1, female as 2. So it becomes numeric. Religion. I can write Hindu as 1, Muslim as 2, Sikh as 3, Christian as 4. Or you can write Sikh as 1, Muslim as 2, Hindu as 3, Christian as 4. Doesn't make any difference. It is simply a label. But this type of data is again easily convertible into numeric form. Similarly, socioeconomic class, lower class, middle class, upper class, I can write 1, 2, 3. So different colors can be coded. So this kind of data, which is easily convertible into numeric form, also comes under structured data. So what is basically structured data? Either it is already in the numeric form, like height, weight, blood pressure, etc., or easily convertible into numeric form. That type of data comes under what is called structured data. Then there is unstructured data. What is unstructured data? Unstructured data is the one where features are not easy to extract. For example, everybody is using WhatsApp. You are receiving hundreds of messages, videos, pictures every day. Now, even at the end of the day, I ask you to convert the entire information into numeric form. I don't think it's easy for anyone. But information is there. People are talking about something. So this kind of data, which is not in the numeric form, but it in the textual form, comes under what is called unstructured data. And people also talk about big data. Big data is nothing but some part may be structured and some part may be unstructured. But as far as this program is concerned, we will focus only on structured data because unstructured data is a difficult task. 2 of my students from bioinformatics, 2 from statistics, they have completed their PhD on unstructured data. But we will focus only on structured data today. That means the data which is on numeric form. And if you look at any kind of structured data, it is basically of 2 types. Either it is called categorical data or it's called measurement data. What do you mean by categorical data? Already given you examples of category like gender. Gender is just a category. You can write 1 and 2 for male and female. Similarly, socioeconomic class is just a category. Lower class, middle class, upper class, you can write 1, 2, 3. Similarly, education categories can be, say, primary school 1, middle school 2, high school 3, graduate, postgraduate. So all this kind of data, which is easily convertible into a numeric form by assigning certain codes, comes under what is called categorical data. Measurement data means some kind of instrument is being involved in measuring something. For example, you can measure height, weight, blood pressure, cholesterol. But sometimes you don't require any instrument, but still it could be a measurable quantity. For example, to measure age, we don't require any instrument. But age can be measured in years. You can add months, minutes, days, minutes, and seconds. So it's a complete measurement, right? So hopefully you are clear about the nature and types of data. Now, once you are clear about the nature and types of data, I'll just go through some of the examples of categorical data like hair color. Hair color could be brown, it could be red, black. So I can write 1, 2, 3. If there is a white also, you can write that as 4. Generally, I avoid writing white because sometimes people get depressed. Our entire body is made up of 4 types of nucleotides. They are known as ATGC. So I can write A as 1, T as 2, G as 3, C as 4. Eye color can be coded as 1, 2, 3, 4. Gender 1, 2. Disease mild, moderate, severe. You can write 1, 2, 3. Similarly, genotypes, depending upon which one is dominant, which one is recessive, the different alleles can be coded as 0, 1, and 2. If it is small hh, it is 0. If it is capital H and small h, it is 1. If both of them are dominant, that means H and H, then it is 2. So all this kind of data, which was in the form of certain labels, is easily convertible into numeric form, comes under what is called structured data. Sorry, categorical data. Measurement data is self-explanatory, like cholesterol, height, weight. Now, if you look at any kind of measurement data, it is basically of 2 types. Either it is called a discrete measurement or sometimes it is called continuous measurement. Now, what do you mean by, what is the difference between discrete and continuous? Discrete means if your data is capable of taking certain isolated values, then it is called a discrete measurement. For example, number of members in a family. Number of members in a family may be 5 members, 7 members, 3 members, but I cannot say number of members in a family is 4.87. It doesn't make any sense. Similarly, number of errors in the book, number of students present in the class. So all this kind of data comes under what is called discrete measurement data. And what is a continuous measurement data? Continuous measurement means it is capable of taking all values within certain specified range. For example, height can take all values in decimals also, 157.5, 157.57 centimeter. You can go to third, fourth decimals depending upon the accuracy of your instrument. So all this kind of data comes under what is called continuous measurement data. That means continuous measurement means it is capable of taking all values, while discrete means it is capable of taking only certain specific values. This is what we mean by discrete or continuous measurement. Okay. So far we discussed that there is a categorical data, there is a measurement data. If you look at categorical data, it is in terms of two different scales. One is called nominal scale, another is called ordinal scale. And if you look at the measurement data, it is also in terms of two different scales. One is called interval scale, another is called the ratio scale. Now, first of all, I'll discuss about the categorical data scales. Categorical data scales are basically nominal and ordinal. And people get confused sometimes between nominal and ordinal. So I'll just take 2-3 minutes to clarify. What do you mean by nominal scale? Nominal scale means, of course, it's a categorical data. There are categories. If all the categories are given equal weightage, then we say that our data belongs to the nominal scale. For example, gender. Everybody is human being. I can write male as 1, female as 2, or you can write female as 1, male as 2. Doesn't make any difference. You cannot say that this will come first or this will come later. So all the categories are given equal weightage. So our data belongs to the nominal scale. Similarly, religion. You can write Christian as 1, Hindu as 2, Muslim as 3, or Sikh as 4, or you can write Hindu as 1, Muslim as 2, Sikh as 3, Christian as 4. Doesn't make any difference. Everybody is human being, right? So this kind of data also comes under nominal scale. So bottom line is, if all the categories are given equal weightage, then we say that our data belongs to the nominal scale. As simple as that. Again, for categorical data, there is another scale, which is called ordinal scale. Ordinal means you can order the categories, although it's a categorical data, but you can order the categories from the lowest to the highest. From, for example, education categories. If I'm writing, say, primary as 1, middle as 2, high school as 3, graduate as 4, postgraduate as 5. So you can arrange all these categories in order from the lowest to the highest or from the highest to the lowest. This kind of data, although it's categories simply, but categories can be arranged in order from the lowest to the highest or reverse order. This kind of data comes under what is called ordinal scale. Similarly, severity of disease, mild, moderate, severe. Similarly, you can socioeconomic class, lower class as 1, middle class as 2, upper class as 3. So 1 means the lower income group, 3 means the higher income group. So this kind of data comes under what is called ordinal scale. Now, if you look at the nominal scale or you look at the ordinal scale, the numerical distance between any two categories doesn't have any significance at all. For example, if I'm writing male as 1, female as 2, subtract 2 minus 1. It doesn't have any meaning at all. Similarly, if I'm writing, say, lower class as 1, middle class as 2, upper class as 3, subtract 3 minus 1 or 3 minus 2. It doesn't have any meaning at all. So please remember, whenever we deal with the ordinal and nominal scale, sometimes these mathematical operations like plus or minus, or if you're making a subtraction, etc., doesn't make any significance at all. So you have to be very careful. That's all about the categorical data. Then we move on to measurement data. Measurement data is also in terms of two different scales. One is called interval scale and another is called ratio scale. Now, people also get confused between interval and ratio scale. Now, what do you mean by interval scale? In interval scale, sometimes the mathematical operations may not be valid. And there are many types of data where mathematical operations are not valid. For example, let's say if some beauty contest is going on and there are judges, say, giving score out of 10. Let's say first person gets a score of 8 out of 10 and second one gets a score of 4 out of 10, right? First person gets a score of 8, second one gets a score of 4 out of 10. Now, if I divide 8 by 4, answer will be 2. But I cannot make a statement that the person whose score is 8 is exactly twice the beautiful than the person whose score is 4, right? Similarly, let's say one student has scored 30 marks. Another student has scored 90 marks. Divide 90 by 30. Answer is 3. But I cannot make a statement that the person whose score is, or the student whose score is 90 is exactly 3 times the intelligent than the student whose score is 30. He may be intelligent in sports or in some other category. So sometimes you can see the mathematical operations are not valid. And moreover, in interval scale, 0 always has a meaning. 0 always has a meaning. That's why in interval scale, 0 is considered as an arbitrary 0, not the true 0. For example, if I say temperature 0, it doesn't mean the temperature doesn't exist. It is still better than -5. Today it is very cold, right? So 0 has a meaning. Similarly, if somebody scored 0 in a test, it does not mean the person is not intelligent at all. Maybe on a particular day, his or her performance is not up to the mark. Next time he or she can score better. So remember, in interval scale, 0 has a meaning. Now, there are problems with each and every kind of scale. To overcome all such difficulties, there is a highest rating scale, and that is called the ratio scale, where all mathematical operations are valid. For example, if some person is having weight 90 kg, another is having 45 kg, divide 90 by 45, answer is 2. But I can always make a statement that the person whose weight is 90 kg is double the weight of the person whose weight is 45 kg. Nothing wrong with that. So you can divide, you can multiply. But remember, whenever we come across 0 in ratio scale, that means the quantity does not exist. While 0, if it is in interval scale, it exists, like temperature 0 exists, marks 0 exist. But in ratio scale, if I say height 0, it doesn't exist. Weight 0, it doesn't exist. BMI 0, it doesn't exist. Body mass index I am talking about. So you have to be very careful. Our data belongs to which kind of scale. And many of the softwares like R, SPSS, Python, they will ask you, your data belongs to which kind of scale. So remember, there are 2 scales for categorical data, nominal and ordinal, 2 scales for measurement data, interval and ratio. So with this background, a little bit of background about measurement scales and different types of variables, I'll move on to my my topic, that is called estimation and testing of hypothesis. And if you have any question, any query at any time point, please don't interrupt me. You can interrupt me anytime and don't wait till the end of the lecture. So anything, to any participant, if it is not clear, you are most welcome to ask any question. Yes, please. Is this clear? Hello?
Excuse me,
Yes,
sir.
sir.
Sir, I have a query, sir.
Yeah, please ask.
Likert scale of form, that Likert scale of item that will come under interval scale or
Yeah.
ordinal scale, sir.
I'll come to. For example, if Likert scale, it is, let's say, strongly disagree to strongly agree. People use 5-point scale, right? People also use semantic 7-point scale. People also use 10-point scale. But you can always arrange those categories in order. Very unsatisfied to very satisfied. That means lowest to the highest level of satisfaction. Very, I'm very strongly disagree to strongly agree. So that means from very low point of disagree to high point of. So all these categories can be arranged in order. So obviously this kind of data comes under ordinal scale. Is it clear? Hello?
Yes, sir. Thank you, sir.
Yeah. Any other question anybody is having? Now I'll moving on to my topic of estimation and
One
testing.
question.
Yes, please, madam.
Sir, in the SPSS, when we are inputting any data, if we arrange the nominal or ordinal or any scale, if we wrongly arrange or wrongly select any scale, then it will it affect our result?
Yes, sometimes, because let me tell you, if you're preparing pivotal tables or custom tables, sometimes if your data is not properly in the categorical form or in the measurement data form, then tables are difficult to produce. And sometimes SPSS give you a warning. For example, let's say you are entering male as 1, female as 2, right? And you give the command that you compute mean. Now, if you compute mean, if data is 1 and 2, if you are not writing that this data is on a nominal scale, if you're writing it is on interval scale, it will compute mean, it will compute SD, right? But that doesn't have any meaning at all. So whenever we specify our data in SPSS, there is a button there. You have to specify your data belongs to which kind of scale, right? So nominal, ordinal, you must properly specify. If you properly specify, then you will not face any difficulty. Is this clear?
Okay. Yes,
Yeah.
sir.
Yeah. So now let me move on to the main topic of today, estimation and testing of hypotheses. As I mentioned that there are 3 words. One is estimation, another is testing, and the third one is hypothesis. So if you look at estimation and testing of hypotheses, so I'll give you a complete picture today, and with practical examples, I'll solve problems on SPSS and give you a practical demo, how to apply t-test, how to compute ANOVA, all these things I'll try to cover today. First of all, the first word, that is called estimation. So let me go through what is called statistical estimation. See, there is always some kind of population. For example, population of doctors in the entire country, it's one population. Population of students in the entire country, it's another population. Even population of students in a particular university is also a population. So some kind of population is always there. But it is difficult to study the entire population. Very difficult to study the entire population. For example, if there are, let's say, 25,000 students in a university, I ask you to compute simply mean height. Now, even then, this simple problem becomes difficult because you go to one department, if there are 150 students, maybe 5 students are not present. You go to another department, 10 students are absent. So it's very difficult to go through the entire population. That's why we take a sample out of this population. Then what we do, we take a sample out of this population, and generally we take a random sample. What is the meaning of this word random? I have written here. The meaning of word this random is every member of the population, if it has the same chance of being selected in the sample, then this is called a random sample. So where the word random means equal probability of selecting an item from a population to the sample. This is what do you mean by random sample. Let me give you one example of, let's say, suppose in a class there are 30 students and somebody give me this task that you have to select 5. Now maybe I know the name of 5-6 students. So if I go by the name selection, there may be favoritism involved, there may be biasness involved. So it's not a random sample then. What could have been the better procedure? That I write down the name of each and every student on a piece of paper, mix them thoroughly, and then take out one slip at random. Whosoever name appears, that person gets selected. This is what we mean by random selection. So we generally take a sample, generally, not necessarily always, but generally take a random sample. So that every member of the population has the same chance of being selected into the sample. Now there are 2 things here. One is a population, another is a sample, and sample is a part of population provided it is representing the entire population. That's why there are different sampling techniques, so that your sample should represent the entire population. Okay, that I'll discuss now. Before coming to the sampling techniques, look at the population. Your values could be associated with the population. Your values could also be associated with the sample. Suppose your population is 1 lakh people, and I take a sample of 500, x1, x2, x500, and I ask you to compute mean of 500 observation. You can easily compute. So add 500, divide by 500, you will get sample mean. Similarly, you can compute sample variance by using the method of variance. That is called S square. You can also, in 500 a sample, you can also see how many males and how many females are there. So sample proportions can be computed, or how many people belong to a particular group. like how many are Hindu or how many are Muslim. So proportions can be easily computed, right? So if your values are concerned with the sample, listen to me carefully, please. If your values are concerned with the sample, then it is called a statistic. For example, X bar, generally we write sample mean as X bar. X bar is a statistic. S square is a statistic. Small p, which is a sample proportion, is also a statistic. So if you remember, if your values are concerned with the sample, then it is called a statistic. And if your values are concerned with the population, then it is called a parameter. For example, there will be a population mean. We have a standard notation for population mean that is called mu. This symbol is called mu. We have a standard notation for population variance, which is called sigma square. Standard notation for population proportion, which is capital P. Sample proportion is small p, population proportion is capital P, right? So if your values are concerned with the population, they are known as parameters. Values are concerned with the sample, it is called a statistic. Now, which values are known to us? Obviously, sample statistics are known to us because we can compute mean, we can compute variance, we can compute proportion. Population parameters are generally unknown. Because it is difficult to study the entire population. But what is our aim? Our aim is to estimate the parameters of the population. Listen to me carefully, please. Our aim is to estimate the parameters of the population based on the sample. And we are referring back from the sample to the population. And this problem is basically called estimation. That is referred to as a statistical estimation. Hopefully you understand this part. Yes, please. Is this okay?
Yes, sir.
Yeah, good. Now, if you look at, once you have looked into the estimation, for example, let's say if you have taken the appropriate sample size, because there are methods to compute sample size. So if you have taken the appropriate sample size, you have also used the appropriate sampling technique, because there are various sampling techniques. Simple random sampling, with replacement, without replacement, stratified sampling, cluster sampling, snowball sampling, judgment sampling, probability sampling, non-probability sampling. There are different types of sampling. They are used in different situations. So if you have used the appropriate sampling techniques, you have taken the appropriate sample size from the population, what you will expect? That this X bar will be closer to this population parameter mean. This sample variance will be closer to the population variance. This sample proportion, which is small p, will be closer to the population proportion, which is capital P. Hopefully you will agree with me. But suppose these are the estimates. This is what you are saying about the estimation. But suppose you have not taken the appropriate sample size, you have not applied the appropriate sampling techniques, and you are driving the estimates based on the sample. Do you think your estimates will be good? They may not be. So next problem comes whenever we have the estimates of the different parameters, whether these estimates are good estimates or these estimates are bad estimates. So that problem comes under what is called testing. So we need to test whether it is good or bad, right? But to test anything, we have to look into what is called hypothesis. So first I'll tell you how to frame the hypothesis, and then we will move on to the testing procedure. Now, before coming to how to take out a sample from the population, we are using different sampling techniques. Of course, we are having one complete semester course on sampling techniques, which is not possible to cover here in 2 hours. But these are the various sampling techniques. I can just give you a brief idea where to use which type of sampling. For example, simple random sampling with replacement and without replacement. They are generally used whenever your population is more or less homogeneous in nature. Homogeneous means they are having the same type of characteristics. For example, if you are going into a class where there are BSc students, say final year students, they are having the same education background, almost of the same age, same characteristics. So this can be considered as a homogeneous population. So simple random sampling with or without replacement are useful whenever we deal with the homogeneous kind of sampling. But population may not be homogeneous always. For example, if you look at West Bengal, there is a one district which is Calcutta. There is another district which are in remote areas, right? Now, if somebody asks you to design, to look into the health status of the entire West Bengal, right? And now you can, let's say, he just allow you to take a sample of size 1000. And now to taking a sample of 1000, you can start in Calcutta, you will end up in Calcutta because there are more than 1000 households in Calcutta only, right? But this Calcutta is not representing the entire West Bengal. There are certain remote districts also, there are other districts also, right? So lack of facilities, they vary from district to district. So obviously this cannot be treated as a homogeneous population. So what you can do, you divide the entire population into different stratas. Let's say I take one district as one strata. So if there are 30 districts in West Bengal, so there will be 30 different stratas, with the assumption that within a particular strata, the population will be more or less homogeneous. And if there is a variability, variability will be only between the stratas. But within a particular strata, the population will be considered as homogeneous. Then I take out a random sample from each and every strata by taking simple random sampling, because population within a strata is homogeneous. So this kind of sampling, now you are taking a sample from each and every district, so it is representative of the entire West Bengal. This is how we look at the representative sample. Then quota sampling and purposive sampling, they are not random samplings. The word random is not involved here, right? Because sometimes our quotas are already fixed. For example, if there is some admission policy, then we know that 15% reserved for SC/ST category, 5% reserved for defense category, 2% reserved for handicapped people, and so on. So once I talk about the reservation, then the probability, random word is gone, probability is gone. So I cannot take more than 5% for defense. I cannot take more than 2% for handicap. I cannot take more than 15% for SC/ST and 16% for 60% for, let's say, general. So I have to be focused on specific quota, right? So this kind of sampling is called, so there may not be equal probability. You understand what I'm saying? So there may not be equal probability. If there is no equal probability, then that means it's not a random sample then. But we require such type of samples also. Now, this type of sampling is called quota sampling, purposive sampling, or judgment sampling. For example, if I want to buy apples, I don't just pick and I'll not go for a random sampling. I use my judgment, whether this is a good piece or it is a bad piece. And I purposely select those which are good ones. So that kind of samplings are called purposive sampling or judgment sampling. Then there is a systematic sampling. Systematic sampling is generally used whenever we deal with large sample surveys. For example, people from NSSO, people from CSO, they are conducting huge surveys. If there is a population of 50 lakh people, they want to survey, let's say, 2 to 3 lakh people. In that type of situation, we use systematic sampling. Then another sampling is probability proportional to size sampling. Probability proportional to size sampling is useful if stratas, you are dividing the entire population into different stratas, and stratas may not be of equal size. Let's say one strata is having a population of 8 lakh, another is having a population of 4 lakh, right? It can happen that one district is having a population of 8 lakh, another district is having a population of 4 lakh. So now in that case, if you are taking 50 units from a population of 4 lakh, virtually you should take 100 units from a population of 8 lakhs. So if you proportionately divide according to the size, then this type of sampling is called probability proportional to size sampling. Similarly, there is a cluster sampling. Cluster sampling also makes sense whenever there are budget constraints, time constraint. We cannot go for each and every selected cluster. Then first we make selection of clusters, and then we go for the random samples. So all these sampling techniques are used in different situations, right? So you need to consult or take the advice of statistical experts that if you are planning some study, that which kind of techniques are available to select a sample out of the population. Yeah, this is what I briefly want to discuss about the sampling techniques. Yes, please. Any problem in sampling techniques? Yes, please. Hello? Is
Hello,
there
sir.
anyone can, is this okay, madam?
Sir, one question.
Yeah, please. Go
Sir,
ahead.
whenever the population size is unknown and we have selected some predetermined criteria for
Hmm.
sample selection, then which sampling technique will be useful?
If your sample size is unknown, many of the softwares, they have two options, you see. Sample size is unknown, and sorry, population size is unknown, population size is known. If you know the sample population size, you can put over there, but generally we go for unknown. And for unknown population, there is a one correction factor. If you apply that correction factor, you will get your corrected sample size, that this is our sample size. So it depends upon the situation. Most of the time, the population is unknown. If the population is unknown, I don't know about the size of the population. So we need to modify our formula of sample size by making some correction factor. And that correction factor we generally add. Hello? Yes, please.
Yes, sir. And which sampling technique will be helpful?
No, it again depends upon. If for every sampling techniques, there is a correction factor. For every sampling techniques, there is a correction factor. Even with replacement, there is a correction factor. Population known, population unknown. Even for stratified, there is a correction factor, known, unknown. So it will depend upon the situation. You follow my
Okay.
point? Yeah.
Yes.
It's not that there is a one formula for unknown and one formula for. So it depends upon which type of sampling you're using, and then look into whether population is known or unknown. All right? Yes?
Yes,
Yes,
sir.
please? Yeah, okay.
So
All
one,
right.
so one question.
Yes, please.
So actually, can I use non-probability sampling technique in case of any experimental research in education?
Depending upon the situation. Let's say if you are come across certain people, let's say you are looking into blind people, okay? And blind students are generally very less. And sometimes you have to go for the entire population. You can study the entire population in that case. So depending upon the situation, and you want to educate these blind people, blind students, I mean. Similarly, there are students who are suffering from a particular disease, right? Like amyotrophic lateral sclerosis, or maybe ALS disease, or maybe some kind of disease, right? So if there are only specific number of students are there, you can study the entire population. Otherwise, you always have to take a sample.
Hello, sir. Sir,
Yes, please.
what is the difference between the quota sampling and the cluster sampling?
Quota
In
sampling, you
agriculture,
see. Yeah, okay.
Quota and cluster, whether both the samplings can be applied in the agriculture sector or taking data from the agriculture fields or from the agriculture research. Purpose
Alright.
is clear. Purpose means where we get our purpose fulfilled. But the two things, quota and cluster,
I'll
why we
explain
can
you.
use quota and why we can use the cluster sampling.
Yeah. I'll explain you. See, in quota sampling, the quotas are already fixed. The quotas are already fixed. But quotas are already fixed in the sense that I already given you example, the 15% reserved for SC/ST category, 5% for defense, 2% for handicap, 1% for some riot victims, and so on. These quotas are already fixed. But in cluster sampling, these quotas are not fixed. You have to make clusters based on your judgment, so that within a particular cluster, the population is more or less homogeneous in nature. So you have to make clusters yourself in cluster sampling, but in quota samplings, quotas are already fixed. Hopefully you understand this part.
So, sir, one more
And in
submission.
cluster sampling, moreover in cluster sampling, one more thing before you ask question. Let's say, I'll give you a simple example. You are talking about agriculture. Now, based on the land holdings of the farmers, suppose I make 20 clusters. Okay. Out of these 20 clusters, let's say 12 clusters, they belong to the big farmers. They are having big land holdings. And 8 clusters, they belong to the small farmers where they are having small land holdings. Now, my budget constraints, my time constraint doesn't allow me to go through all the 20 clusters. But it says that you have to select only 7 clusters. Then proportionately I can divide. Proportionately, how I can divide? Because these 12s are of the similar size, similar type, because they belong to large farmers. These 8 are of the similar size because they belong to small farmers. So proportionately means I'll take 4 from 12 and 3 from 8, and so that I'll study only the 7 clusters, not going through the 20 clusters because of the time and the budget constraints. So this is how we go for the cluster type of sampling. You follow
Sir,
my point?
Hello, sir. One more submission.
Yeah.
We are having here the classification of the farmers. There are the marginal farmers, there are landless farmers, or the farmers who possess more than land. That means quota sampling cannot be applied to that farming.
No. Not the quota sampling. Not the quota sampling. It will come under cluster sampling.
Yeah. It will come.
Yeah.
That means it is not applicable there, whether in the forestry research or the agriculture research.
Yeah. Absolutely right.
Sir, one more thing, sir, regarding purpose of sampling. For example, I am doing some research on the forestry or the agriculture, and purpose means where my purpose is fulfilled.
Yeah. Let me give you. Let's
why
say
my purpose is fulfilled, where my objective is fulfilled, which I can go for there.
no.
Then,
See,
sir,
proposed sampling is sometimes
proportion to size. You have one more thing is there, probability proportional to size population sampling. But how I can correlate it with it?
which one you want to correlate?
Proportional size. What is
Probability
this?
proportional to size sampling is a very simple. For example, I already explained you. For example, in stratified sampling, we generally assume that the out of the total population, the stratas which you are making, they are more or less of equal size. For example, let's say in stratified sampling, let's say one strata is having a population of 4 lakh people, another is having 4,50,000 people, another is having 4,75,000 people. So these stratas are more or less of equal size, right? But in probability proportional to size sampling, your stratas may not be of equal size. Already given you an example. Let's say one strata is having a population of 4 lakh, another is having a population of 8 lakhs, another is having a population of 16 lakhs. Now, if you are taking a sample of 100 from a population of 4 lakh, virtually you should take a sample of 200 from a population of 8 lakhs and 400 from a population of 16 lakh. So if you proportionately divide, then that is called probability proportional to size. You follow my point? Hello?
Okay, sir. Okay, it's clear, sir. Thanks.
Right. Okay. So these are the sampling techniques which are used in different situations to select a sample out of the population. Now, sample versus population is a very, very important concept, because we take a sample in such a way so that it should represent the entire population. Now, whenever we go to a market to buy grapes, this is what the people generally do. They pick up one, they taste it. If it sounds good, they buy it, and sometimes they leave it. Yes or no? Yes, please.
Yes.
Yeah. But if you ask a person from his statistics, he will go one step ahead. He will pick up one from here, another one from here, possibly one more from here. Because what we are looking for a representative sample. Because what happens sometimes, the good ones are always at the top and bad ones are hidden behind. So if you are taking a sample from one corner, it may not give you a very good estimate. So that's why sample versus population is a very, very important concept. You should take a sample in such a way so that it should represent the entire population. But in such type of example, you have to be careful whether the person in front of you will allow you to do this or not. You follow my point? Yeah, please. I ask everyone to mute, please, because there is some noise. Is this okay? All right. Next, again, sample versus population. There was a very senior doctor. And he was teaching the importance of sampling techniques to the junior doctors. And one of the junior doctor didn't get convinced. He says, "Sir, why to look at the sample? Why not to study the entire population?" Then the senior doctor was wise enough, and he took this junior doctor to the nearby patient. And here is a patient you can see. and ask this junior doctor that you take out the entire blood of this patient. The junior doctor said, sir, patient will die. Then the senior doctor asked him what you will do. He says, I'll take a sample. You follow my point? So whenever let's say somebody is having stomach pain, he goes to a doctor. Doctor will not cut his stomach and see what is inside. He will prescribe certain blood test or maybe go for ultrasound or something. And whenever you are giving a blood test, you are not giving the entire blood of your body. You are just giving a sample. That sample represents the entire blood of your body. And based on that, certain estimates of your parameters like hemoglobin, like TLC, DLC, they comes out. Right? SGOT, SGPT, they all come out. And then the doctors have to prescribe the treatment. So try to understand the importance of sample from a population. Hopefully this makes sense to you. Okay. What is a representative sample? Look at this picture and the definition first of all. A sample that represents the characteristics of the population as closely as possible. As closely as possible. So there is a picture of a kangaroo. There is a picture of a baby. So here baby represents the entire characteristics of the mother. So this baby can be considered as a representative sample. But suppose, and this is a target population, but suppose I replace this baby with a baby of a dog or a cat. Do you think it will be a representative sample? It won't be a representative sample then, right? So this is what do you mean by representative sample. With this background, how to take out a sample from the population, let me move on to now testing of hypothesis. These are the learning objectives in this class: to understand the role of significance test, to distinguish between null and alternative hypothesis, critical region, level of significance, to interpret the p-value, type 1 and type 2 errors. So all this I'm going to cover. And after that, I'll give you a practical demonstration in last 45 minutes because our class is up to 4:30. So just bear with me at the theoretical part because these things are not explained in most of the books. So I'll go through these concepts and then give you a practical demo. Okay, what is a hypothesis? Now, some people say there is a negative hypothesis, there is a positive hypothesis. Let me tell you, there is no concept of negative and positive hypothesis in statistics. What is a hypothesis? Look at this definition. A tentative statement regarding the population, not regarding the sample, because you cannot study the entire population. So you have to make inferences about the population based on the sample. So the tentative statement regarding the population relating to a certain phenomena, means relating to height, relating to weight, relating to BMI, in which the researcher is interested and wants to verify on the basis of the sample. So that means if you put your objectives of your study into 1 or 2 sentences, that basically becomes your hypothesis. So these hypotheses are basically 2 types. One is called null hypothesis, another is called alternative hypothesis. So let me take a true example because time is running. So let's say somebody is interested in testing that the mean IQ of this population is likely to be 100. Now that is the claim the person is having, that the mean IQ of this population is likely to be 100. So whatever is the mean, whatever is the claim, you always put under H0. So that is his claim, that the mean IQ of a population is likely to be 100. Now what is the, you see, in under H0, null hypothesis is denoted by H0. Alternative hypothesis is denoted by H1 or HA. One and the same thing. A stands for alternative because we are writing under H0 0. So sometimes we write 1. 1 means alternative hypothesis, right? Now, why I have used the symbol mean mu? Because I am referring to mean IQ of a population. And in the, if you remember, there are population parameters. Population mean is mu. Population variance is sigma square. Population proportion is capital P. So from that angle, I am writing this, that mu is equal to 100. Mu means what is your study variable? Your study variable is basically IQ, right? So I'm interested to test that the mean IQ of this population is 100. So that's why I'm writing mu is equal to mu naught, where mu naught is given to be 100. So it is specified. Okay. Now this, whatever the claim, we always write under H0. Now, Once we have framed the, for example, its H0 may not be fixed. For example, if somebody is interested in testing that the mean weight of a certain population is 60 kg, that is the claim, then you can write mu is equal to 60 kg. If he is interested in testing mean height is 157 centimeter, then it will be mean is equal to 157 centimeter. If he is interested in testing not mean but variance, the variance of this population is likely to be, say, 7. Variance of this population is likely to be 7. Then hypothesis will change. I will not put mean now because we are asking about variance. So sigma square will be equal to 7 in that case. If somebody says that 40% of this population is likely to vote for this party, 40% of the population is likely to vote for this party. Now we are talking about proportion. 40% means 0.40. So hypothesis will again change. I'll write H0 capital P is equal to 0.40. So depending upon this situation, we have to frame whether we are concerning with mean, whether we are concerning with variance, whether we are concerning with proportion, or sometimes you can even frame the hypothesis for two populations. Let's say somebody wants to see that the performance of government school and convent school is the same. So if the parameter of the government school is mu1, parameter of the convent school is mu2, then hypothesis can be framed. If the performances are equal, then hypothesis will be mu1 is equal to mu2. Mu1 will be equal to mu2. So depending upon the situation, we have to frame our null hypothesis. Now, to every null hypothesis, there may be different alternative hypotheses. There may be different alternative hypotheses. So one of the, if I'm testing mu is equal to 100, one of the alternative could be that it is not equal to 100. So it's not equal to 100. Now, if it is not equal to 100, I am not sure whether it is less than 100 or it is more than 100. No idea what will happen in the population. So this type of alternative where not equal to is written is called two-sided alternative. Why two-sided? Because I am not sure whether it is mu less than 100 or it is more than 100. So that's why it is called two-sided alternative. But sometimes person is 100% sure that this is a very good population. I am 100% sure the mean IQ of this population will be, these students, very good students, mean IQ of these students definitely will be more than 100. So person is 100% sure. Then alternative will change. You will write mu greater than 100. And if somebody is 100% sure, I know these students, they are very dull students. I know their mean IQ cannot be 100. Not at all. Forget about this. Person is 100% sure. Again, the hypothesis will change. So you will write mu less than 100. But under H0, there will be always equal to sign. Under H0, there will be always equal to sign. Depending upon what the person is testing, will be under H0. H0. And then alternative you have to think of. If the person is 100% sure about something, use one-sided. If person is not sure what will happen in the population, use two-sided. Let me give you an example. People get confused where to use one-sided, where to use two-sided. In 80 to 90% of the cases, people use two-sided. Why? Because we don't know what will happen in the population. Person is having claim that hemoglobin of this population is likely to be 11.4. That is a claim. I don't know what will happen in the population. It could be less than, it could be more than 11.4. So I'll use two-sided to be on the safe side. But if somebody is know that this population, most of them, they are having low hemoglobin level, person is 100% sure that their hemoglobin level will be less than 11.4. Then in that case, I'll use one-sided. Let me give you an example of one-sided. Suppose patient comes to the doctor. Doctor examines their blood pressure. And let's suppose all these people are suffering from low BP, low blood pressure. And doctor knows there are standard medicines available in the market. People are using for the last 30, 40 years. He asks them to consume the medicines for 3 months and call the same patients say after 3 months. Now, when the same patients are coming after consuming the medicine after 3 months, what the doctors will expect? He will expect that this time their blood pressure, low BP problem should come back to normal. It should increase, right? So in that case, the doctor is 100% sure because these are very well tested medicines. People are using for the last so many years. Clinical trials have been done. So in that case, we will be using one-sided. Otherwise, we generally use two-sided. So hopefully this makes sense to you. What do you mean what do you mean by one-sided? What do you mean by two-sided? But look at this thing. This alternative is greater than is also one-sided, less than is also one-sided. To distinguish between greater and less, we write this as one-sided because it is greater. Greater means right-hand side. So we call this as one-sided right-tailed. Less than means on the left-hand side, we call this as one-sided left-tail alternative. Right? Okay. Let's come to type 1 and type 2 errors. What are type 1 and type 2 errors? See, what is written in green line is very important. No study is perfect. There are always chances of error. Now you know what is H0, what is alternative. For example, here is the decision. Here is H0 is true, H0 is false. H0 is true means something is of good quality. H0 false means something is of bad quality. Try to learn this. Then you have to take a decision. So how to this? Reject H0 when H0 is true. What does this mean? Something is of good quality, but it has been rejected. Something is of good quality. H0 is true. Something is of good quality, but it has been rejected. This is called type 1 error. What is type 2 error? H0 is false. Accept H0. Something is of bad quality, and you are going to accept that. That is type 2 error. That is type 2 error. Right? Let me give you an example of type 1 error. Type 1 error happens in many situations, particularly in selection procedures. There is a good candidate and there is another candidate having pull or push. And sometimes the good candidate are rejected. H0 was true, but it has been rejected. And the pull and push person has been selected. Then the university or the college have to suffer for how many years? 30, 40 years, 30 years. Because dad would plant it for 30 years. Hopefully you understand what I'm trying to say. Because type 1 error has been committed right in the beginning. So you have to be very careful. What is type 2 error? Accept H0 when H0 is false. You want to buy apples. You went to the market. Apples, you can see at the face that apples are not of good quality. But the owner says, sir, you have to just buy 1 kg, just pick and choose. So I just use my judgment, pick and choose. Bring 1 kg at home. Consume, my entire family consume that. And we got food poisoning. Doctor has charged me 10,000 rupees. Whose loss is this? That's my loss. Because I accepted a bad lot. That type of error is called type 2 error. So accept H0 when H0 is false is type 2 error. What could have been the correct decision? Correct decision is reject H0 when H0 is false. Something is of bad quality and you also rejected. That's a correct decision. What's another correct decision? H0 is true and you accept that. Something is of good quality, you also accepted. That is a correct decision. So this diagonal, they are type 1 and type 2 error. Off diagonal, they are correct decisions. Let me give you 1 or 2 more examples of type 1 and type 2 error. This is another example from medical test. Medical test type 1 error is called false positive. Type 2 error is called false negative. What is false positive? The person doesn't have a disease, but the test says they do have. Now, when COVID-19 emerges right in the beginning, there was no testing procedure. And 30% of the cases, let me tell you frankly, 30% of the cases, they were false positive. The person was not having any disease, but the test was saying they were having, they were put into the hospitals, and even they were not having the disease, they got the disease. That was the result of type 1 error. So person doesn't have a disease, but the test says they do have. And what is type 2 error? The person has a disease. He is having COVID-19, but the test doesn't pick it up. He comes home, there are 5 members in the family, all of them affected. They all got COVID-19 because it's a type 2 error. That's called false negative. Look at the court example. Convicting an innocent person. Person doesn't have any done any crime, but judge has convicted him. Type 1 error. What is type 2 error? More serious. Not convicting the guilty. The person has done a crime, but the judge has let him go. He may kill a lot of other people's. Not convicting the guilty. That is type 2 error. So you can see various examples from court example, medical example, journal examples. So all these 2 types of errors are very serious, and we need to have a control on these 2 types of errors, right? Generally, we fix type 1 error and try to minimize type 2 error. Okay, then comes what is called level of significance. You must have gone through many of the research papers. People write 5% level of significance, 1% level of significance. That probability of type 1 error, probability, because we want these errors to be small. Probability of type 1 error is basically called size of type 1 error. Probability of type 1 error is called size of type 1 error. And maximum level which you can afford is called a level. You cannot go beyond this level. For example, let's say if I give you a basket, there are 100 apples and 40 are of good quality and 60 are of bad quality. You will accept that lot? You will never accept that lot. You will say, they are of, I'll not take this basket. Because a lot of bad quality apples are there. But suppose 1 or 2 pieces are of bad quality, rest of them are okay. Still you can accept that lot. But there has to be certain limit. That maximum allowable limit in statistics is 5%. That's why we call this as level of significance. That means if out of 100, up to 5 are of bad quality, still I can accept that lot. But if it is beyond that, I will reject this lot. This is what do you mean by level of significance. And level of significance is always fixed in advance before going for the analysis, right? Generally, the level of significance depends upon the type of study we are conducting. Generally, we take 5%, 1%, right? Probability of type 2 error is called beta, which is generally called size of type 2 error. Type 2 error is not as such important, but 1 minus type 2 error, probability of type 2 error is called 1 minus beta, which is called power of the test. And it is directly related to the sample size. It is also directly related to the sampling techniques. For example, if you have not taken the appropriate sample size, you have not used the appropriate sampling technique, then the power of your t-test, power of your ANOVA will come down. So that's why 1 minus beta generally is computed to check the power of the test. Then there is a concept of p-value. We frame the null hypothesis, we frame the alternative hypothesis, and we reject the null hypothesis if your p-value is less than or equal to alpha. Alpha is already selected, 5%, 1%, right? So please remember, p-value is given by the software. Alpha you have already fixed. H0 you have to write down. Alternative you have to write down, and reject H0 if your p is less than or equal to alpha. Then we generally reject H0. So I'll explain you the concept of p-value later on. But before coming to the p-value, for the time being, you simply remember that we reject H0 when p is less than alpha. So first of all, I'll go for the parametric test, then I'll cover up some non-parametric test also. Where to apply parametric test? We apply parametric test whenever our data follows or data comes from normal distribution. What is a normal distribution? How to check the normality of the data? Everybody knows about histogram. Now, if your histogram is more or less symmetrical in nature, then we say that data comes from normal distribution. Or you can look into box plot. Box plot is another way to look into normality of the data. This is called median line. This is called the lower end of the box. This is called the upper end of the box. Lower end is placed against Q1. That is called first quartile. Upper end is placed against Q3. That is called third quartile. Then there is a box between first and third quartile. And then there is a whisker which connects to the lowest value present in the data from the middle portion, lower part, and from the upper part, from the middle portion, connect to the highest value present in the data. And this plot is called box and whisker plot. Box and whisker plot. It is helpful in checking the normality of the data. So if your median lies exactly in the center of the box, if median lies exactly in the center of the box, this is called median line. Then we say that our data is normally distributed. But look at this thing. How this is a normal curve. If your data would have been normal, all these bars which are going outside this curve, they should be within this curve. If they are all within the curve, then you say that your data is normally distributed. Now, how to read this? you drop a line from the highest bar. Drop a line from the highest bar and count how many bars on the left hand side. 1, 2, 3. But how many bars on the right hand side? Maybe 8 or 9. So this data, which is having more values on the right hand side, is called positively skewed. It's called positively skewed. So it simply says that your data is not normally distributed. For the same data, this box plot also says the same thing. And the third plot is called quantile plot. Quantile plot, it computes the quantile of your data. This is a standard normal quantile line. If your data would have been following a normal distribution, all these dotted dots, they must be on this line, but they are away from this line. That means the data is not following a normal distribution. So these three graphs are very important: histogram, box plot, QQ plot. QQ plot is sometimes also called normal quantile plot. It is written normal QQ plot, right? So these, with the help of these three, you can check the normality of the data: histogram, box and whisker plot, quantile plot. And there are tests also: Kolmogorov-Smirnov test, Sparrow-Wilk test. These tests are also helpful to check the normality of the data. Once we establish that the data comes from normal distribution, our hypothesis H0, H1, they involve population parameters like mu is equal to something, or sigma square equal to something, or mu1 is equal to mu2. Then we go for parametric test. So parametric tests are applicable only when data comes from normal distribution, right? Okay. Now there are two types of parametric tests. They are used for large samples. They are used for small samples. But in many of the softwares, only small sample tests are given. And that is in terms of t-test. So t-test can be used for testing single population mean, difference of two population means, for paired data, even for checking the correlation coefficient, significance of correlation coefficient, we use t-test. Testing the equality of variances, we use f-test. And more than two variances, there are Bartlett test. More than two means, if you want to compare 3, 4 populations in terms of means, then there is one-way, two-way, other types of tests are also there. But in most of the softwares, only t-test is given, not z-test. Z-test is for large samples, t-test is for small sample. Why in many of the softwares only t-test is given? Let me explain you. Because generally sample size which is more than 30 is considered to be large sample, less than 30 is considered to be small sample, right? So if your sample size is 12, 15, 20, so it's a small sample. So you have to get the value of t-test. But this t-test approaches to z-test when your sample size becomes more than 30. What does this mean? Because t-test can be applied for small samples, and when sample size becomes large, your t-test basically approaches to z-test. So whether you give your inference based on z-test or t-test, you will get the same result. So that's why in many of the softwares, only t-test is given. It can be applied to small sample. It can also be applied to large samples, right? So first of all, we'll go for the t-test. So here there are few examples where to apply t-test. So I'll give you a practical demonstration also. For example, there are 3 types of t-test. One is called one sample t-test. Another is called independent t-test. Third one is called paired t-test. Now, when to use one sample t-test? If somebody is having certain claim that weight of this population is likely to be 60 kg. Mean weight of this population is likely to be 60 kg. So I'll frame the hypothesis. Parameter of the mean is mu. So I'll frame the hypothesis H0, mu is equal to 60 kg. Alternative, mu not equal to 60 kg. Because I am not sure whether it is in the population, it is going to be less than 60 or more than. So I'll be playing safe, not equal to 60 kg. Now we have to take only one sample. Which sample? So if there is a population, I'll just take a sample of, let's say, 250 people, note down their weights, and based on their weights of 250 sample, I'll test this hypothesis, whether the population is having this weight or not, right? This is called one sample because there is only one variable, that is weight. But sometimes, does the mean weight differs in 2 regions? For example, one of the state is Assam, another is West Bengal. Now people want to see whether the mean weight of, let's say, male populations, they are same or they are different. So I'll take a sample of, let's say, 1000 people from West Bengal, sample of maybe 1500 from Assam, right? And want to compare them and note down their weights, right? So my hypothesis will be, if mu1 parameter stands for West Bengal, mu2 stands for Assam. So if there is no significant difference between the weights, so I'll expect H0 that mu1 will be equal to mu2. So I'm testing this hypothesis against the alternative that mu1 may not be equal to mu2, because I'm not sure whether they are small people, whether they are having more weight or they are having less weight. No idea, right? Similarly, t-test can also be used for testing the medicine effect. Let's say doctor visit the patients, doctor note down their blood pressure, and they are, let's say, all of them, they are suffering from low BP problem. That is, before giving the treatment, their blood pressures are before giving the medicine. Then doctor give them medicine, call the patients after 3 months. They are the same patients. They are not independent like Assam or West Bengal. They are same set of patients. And one reading will be before giving the medicine, another will be after giving the medicine. So if the treatment is effective, suppose I test this hypothesis that there is no significant difference in means. D stands for difference, that before and after means are 0. That means the medicine is not effective. So I should reject this hypothesis for a medicine to be effective. Otherwise, the differences in before and after, they are 0. That means it is not effective at all. Hopefully you understand this part. So t-test is used. There are 3 types of t-test: one sample t-test, independent t-test, pair t-test, right? So just to give you a statistics, let's say we want to test mean is equal to 60 kg. Somebody claim this. I take a sample of, suppose, 250 people and compute the sample mean. That is your X bar. So X bar is known to me. I add 250 weights, divide by 250, you will get. Under H0, your mu naught, under H0, because test statistics is always consuming that H0 is true. Under H0, what is your mu naught? Is 60 kg. So you can substitute here 60 kg. X bar is known. Similarly, sample variance you can compute. N is 250. So in all and all, you can compute the value of this statistics. That is T, right? A single sample, n minus 1 degrees of freedom. Why n minus 1 degrees of freedom? Because in computing the sample variance, we are dividing this factor by n minus 1. And those who are from statistics or mathematics, those who are here, there is one concept which is called unbiased estimate. If you take the expected value of this S square, it will come out to be exactly equal to, say, this sigma square. That means it is an unbiased estimate. But if I divide this by 1 over n, then in that case, it will not be equal to unbiased. It will not give you unbiased estimate. So that's why we divide by n minus 1, and that's why the degrees of freedom are n minus 1. So degrees of freedom for T is n minus 1. So this is the test statistics for testing. So let me give you a practical example through SPSS. So I'll take up one file. If you have any question up to this, now I'll be giving you a practical example. If you have any question up to this, you are most welcome to ask, please. Yes, please. Any question? Yes, please. Any question? If you have any question, please, in mind, you can ask me. I'm here now. Yes, please. Somebody want to ask some question? You can unmute and ask. Hello?
Sir, it's fine.
It's fine. Anybody else? It's okay? All right. So now I'll give you a practical demonstration. Can you see this PPT again? Hello?
Yes, sir, we can see.
Okay.
Yes.
All right. So I'm just taking one practical example to apply t-test. Let me just minimize the screen and show you. So I'll take one data set. Just a minute. I'm opening one of the file. So we'll apply one sample t-test. Please have a pen or pencil with you. Please have a pen or pencil with you. Now here is. Now somebody was observing population. Can you see this file? Yes, please. Can you see this data file?
Yes, sir.
All right. See, somebody was observing the population, and he was observing that the people are putting up weight. So idea struck to his mind that people are moving towards obesity or overweight problem. Why not to check their BMI levels? BMI level, you know, can be easily computed based on height and weight. So it is nothing but weight in kg divided by height in meter square. Square is only in the denominator. So if you apply that formula, you will get BMI. So he take a sample of few people from the population and compute their BMI. That is called body mass index. So if you are carrying a pen or pencil, please write down. If BMI is less than or equal to 20, although the cutoff is 18.5, but I am taking roughly less than or equal to 20. If BMI is less than or equal to 20, the person is called underweight. The person is called underweight, that he is having underweight problem. Now, if your BMI level is between 20 to 25, roughly, then it is called normal BMI level. Then it's a normal. It could be 23, it could be 22.5, it could be 24. It's called a normal BMI range. So 20 to 25 is normal. Then 25 to 30 is basically called overweight, overweight. And if person's BMI is more than 30, then the person is suffering from obesity or obese problem. जिसको बोलते हैं मोटापा हिंदी में, right? So he want to test. Now here is a problem. Please listen to me. Here is a problem. Person want to test whether this population has a normal BMI level or these people are moving towards obesity or underweight problem. Hopefully you understand. So under H0, what will frame the hypothesis? Will frame the hypothesis that this population is having normal mean BMI level. Now what is the parameter for mean? Mu. So I will write H0. Mu is equal to, the normal BMI level is range is from 20 to 25. That's a normal range. So you can pick up any value, maybe 22.5, maybe 23, maybe 24. So let me take 24. So I'll frame the hypothesis H0. Mu is equal to 24. Please write down H0. Mu is equal to 24. Alternative H1. Mu not equal to 24. Right? Now suppose I accept the hypothesis. Then there is nothing to worry. People are having normal BMI level because their normal BMI level is around 24. You have accepted the hypothesis. Problem comes when you have rejected the hypothesis. When you have rejected the hypothesis, suppose I reject H0, then you have to be careful whether people are suffering from underweight or they are overweight or they are obesity. Answer to this is given by one sample t-test. So now I'll explain you one sample t-test, how to apply this. Hopefully the problem is clear. Yes, please. Problem is clear.
Yes, clear.
Okay. So go to analysis, go to compare means, and in compare means, this is one sample t-test. Go to one sample t-test. So test variable is BMI. Take this to this side. Test value is that value which you have written under H0. Can you tell me what we have written under H0? Yes, please. Under H0, what we have written?
Mu equal to 24.
So this value is 24. Very good. This value is 24. That's all. It will just take 1 minute to click away and press OK, and you will get T value and P value. And you just have to focus on P value. So press OK. So here is the result. It says you have taken a sample of size 25 people. This is the mean weight. And this is the standard deviation. That is SX square. And if you divide standard deviation by under root of mean, you will get standard error of mean. I mean, if you divide 7.003, divide by under root of 25. Under root of 25 is 5. So if you divide 7.003 by 5, you will get this quantity. And how do we compute mean? Mean is nothing but in the numerator difference, x bar minus mu naught. Your mu naught is 24. X bar is 31.04. So numerator will be 31.04 minus 24 divided by standard error, 1.401. If you do all the calculations, you will get this t value. And degree of freedom is always 1 less than the number of observations. So your observations are 25, degree of freedom is 24. And this is your p value. So p value says your p value. Wherever it is written significance in SPSS, that means it is a p value. So your p value is 0.000. Basically, p value is never 0, let me tell you. P value is never 0. If it is coming with 3 zeros, you always put 1. But I can prove that why this is not 0. If you double click here, just let me double click. This is double click and right click, go to the table properties or cell properties, and in cell properties, go to the format value, and in format value, go to the number and increase the decimals. Let's say I make this instead of 3 decimals, because SPSS give you p value up to 3 decimals. Suppose I give the decimals 13, press OK. This is actually the p value. Now you can see the exact p value. P value is never 0, right? Even after 50 decimals, something can come over, because graph of normal distribution never touches the x-axis, never. So this is your p value. So here p value is less than 0.05. Now you remember my PPT, when to reject h naught. So x bar is known, mu naught is known. This denominator is standard error. Denominator is nothing but standard error, right? Okay, so you have computed this and reject h naught. If you remember this slide, reject the null hypothesis if p is less than alpha. Your alpha was 0.05. P value is 0.000 something, which you have gotten this one. So your p value is less than alpha. Yes, please. Whether you will reject the hypothesis or accept. Yes, madam. Whether you will accept the hypothesis or reject. Yes, please. Anybody?
Reject.
Reject. You will reject.
Reject
You will
them.
reject the hypothesis. Why? Because your p value is less than alpha. If p value would have been greater than alpha, you accept. As simple as that. So rejecting the hypothesis means, what was your hypothesis? We reject the null hypothesis only. We reject the null hypothesis. What was your null hypothesis, madam? Mu is equal to?
24.
24. So it has been rejected. That means alternative will be accepted. What was the alternative?
Mu is not equal to 24.
So one thing this t-test says, that your mu is not equal to 24. That means these people are not having normal BMI level. One thing is clear. But I don't know whether they are having underweight or overweight problem. Look at the mean. What is the mean value here? Yes, please. Can you tell me what is the mean here, madam?
31.4.
31.4. Yeah, 30. So it is beyond 30. Yes, it is beyond 30.
Yes.
And beyond 30 means people are suffering from?
Yes.
People are suffering from obesity problem. So entire crux of doing this exercise is that people are not having normal BMI level. They are not having underweight problem. They are not having overweight problem. But in fact, they are having obesity problem. You follow my point? Hello?
Yes.
Yes, sir.
That is the entire exercise you have done. That you have to ask people, please do not eat pizza, burger, noodles. Your weight is increasing. In US, the obesity rate is around 64%. In India, it's around 16%. It is catching up now. In next 5 years, likely to double. So you have to be very careful. All right. So this is one sample t-test. Hopefully you know where to apply one sample t-test. Now we go for two sample t-test. Two sample t-test is also called independent t-test. Independent t-test or student t-test, or sometimes also called two sample t-test. One and the same thing. Now where to apply this test? Already given you example of government school children and convent school children, whether their performances are equal or not. So here is an example in PPT that there were two types of diets. One was pizza diet, another was normal diet. Some people put on pizza diet for a week, and some people put on normal diet for the same week. And after a week, They want to check which group is having more weight gain. Which group is having more weight gain. So this is the experiment. So what we are testing here, weight gain due to pizza diet is same as weight gain due to normal diet. That means mu1 is equal to mu2. Against that, mu1 is not equal to mu2. Right? And this is the statistics which we need to compute. So what I'll take say 15 candidates, those who are interested in pizza, 15 those who are interested in normal, or maybe 20, doesn't matter, number may be different. Let's say N1 is your 15, N2 is your 20. Then I can compute mean weight after 1 week of the first, those who have consumed pizza diet, then mean weight after 1 week, those who have consumed the normal diet, take the difference. Then this is their standard deviation from group 1, standard deviation of group 2. Then I compute the pooled standard deviation, substitute this value here, N1, your N1 is 15, N2 is 20, and compute this value of the test statistics. Everything is known. So how to decide about the degrees of freedom? For first sample, degree of freedom is n-1. So in this case, it will be n-1. In second case, it will be n2-1. So if your first sample is having, let's say, 15, so it will be having 14. If second sample is having 20, so it will be 19. Plus 19 is 33 degrees of freedom, right? So in this case, degrees of freedom will be n1 plus n2 minus 2. So let me take a 2 sample example and show it to you how to solve this problem. So I'm just closing this file and take the another file. If you have any question, anything in mind, please don't hesitate to ask. Let me take up the second example now. T-test, independent T-test. Yes, please. Anybody having question?
So we need to check
Normality of the
normally
data.
distributed or not.
Yes, you need to check the normality of the data first, either by plot. All these are normally, actually I have checked in, right? So you can check the normality of the data first of all, and if they are coming from normal distribution, then you apply this test. So now we come to T-test. This is independent T-test. Okay. So if there are independent T-test, please try to understand the concept. There was an industrialist and he wanted to hire people for his industry. And there were 2 types of group. One group, those who have done post-graduation. Another group were undergraduates. Now, problem was clear that if he hire people from less educated people, means undergraduate people, he has to pay less salary. And if he hire people from postgraduate, he has to pay more salary. The idea struck to his mind because the work he has to carry out is a semi-skilled kind of work. Undergraduate people can also do, and postgraduate people can also do. But idea struck to his mind that I will hire intelligent people. That why not to check their BMI levels? Sorry, not BMI, IQ levels. Why not to check their IQ levels? So he has taken the IQ levels of the PG group, then IQ levels of the UG group, and tested the hypothesis that the IQ levels of PG and UG group, they are same. That means he is testing. You can write down, please, H0. Mu1 is equal to mu2. What is mu1? IQ level of PG is equal to IQ level of UG. That is mu1 is equal to mu2. Alternative, mu1 is not equal to mu2. Hopefully you have written the hypothesis. Yes, please. Madam, आपने लिख लिया hypothesis? Hello?
Yes, sir.
Okay, very good. So what is mu1? Mu1 is nothing but IQ level of PG group, and mu2 is nothing but IQ level of UG group. How I feed the data? So these are IQ levels. I put 111 where there is PG, 111. And then after that, IQ levels of 22 group, second number group. And this is how I label the later on. Hopefully you know all these things, that 1 is for PG and 2 is for UG. I think you know this thing. Yes or no? You know how to enter the data in spaces?
Yes, sir.
Okay. All right. So this is UG and PG. So this is your IQ. This is the variable we want to test. All right. So I'll apply, because these are 2 independent populations. one is PG, another is UG. So independent t-test or two sample t-test. So again, go to analysis, go to compare means, and in compare means go to independent t-test. Now it says what is your test variable? Your test variable is the first one, IQ. It says which one is your grouping variable? Your grouping variable is here. It says what is the group name? Group name is 1 and 2. You can have 3 and 4, you can have 6 and 7, doesn't matter. So I have to specify that group number 1 is 1, group number 2 is 2. Continue. That's all. And you will compute this t value. Press OK. Now, there are 27 people in PG, UG 61. These are their mean IQ levels. Standard deviation, standard of mean. This is how the t value is computed. So t value is this, how the degrees of freedom are computed. For first, this is your N1. So N1 minus 1, 27 minus 1, 26, plus 60 minus 1, 60. So 60 plus 26 is 86. So 86, this is the p-value. Now your p-value is 0.001. Is it less than 0.05 or more than? Yes, please.
Less than 0.05.
So if it is less than, if p-value is less than 0.05, we will
Reject the null hypothesis.
reject the null hypothesis. What was the null hypothesis?
Mu1 is equal to mu2.
That means the IQ levels of PG and UG group, they differ because it is rejected, right? They differ. Now, what he was thinking that if their IQ levels are same, he will hire people from UG group. So his claim was absolutely wrong. Now we have to see which group is having better IQ. Go through the mean. What is the mean IQ of PG? 95. What is the mean IQ of UG? 79. So his claim was absolutely wrong. He has to hire people only from PG group. He cannot save his money. That was the entire crux of this exercise, which is called independent t-test. Is the problem clear?
Yes, sir.
All right. So this problem is clear, right? Okay. So now you know where to apply independent t-test if you want to compare any two groups. Now, then we come up to the next slide, which is called paired t-test problem. So this is called paired t-test. Now in paired t-test, basically we want to test that the differences in before and after they are 0. That's why I put mu d. Mu d stands for population mean difference before and after the treatment. So if it is 0, suppose I accept this hypothesis, that there is no effect of medicine, because what was the previous result, later is also having the result. So it's the same. So there is no effect. Same thing you can apply today. For example, right in the beginning, when we started the class at 2:30, suppose I give you a question paper in which there were questions related to hypothesis, questions related to type 1 error, type 2 error, structured, unstructured, at all these questions, and t-test. And I ask you to whatever you want to give your score, you give. So obviously that scores were before giving the training. At 4:30, I'll give you the same questions back. Now, which one will be better? If my training is effective, the after score will be better than before score. Yes or no? Yes, please.
Absolutely, sir.
Absolutely, right? So, but if there is no difference, then the training is not effective. You follow my point?
Yes, sir.
please. Yeah, all right. Now to check this claim, what we do, this is before giving the treatment, this is after giving the treatment. So we subtract all these values, yi minus xi, and you will get a single value now, differences. Then you compute the mean of the differences, you compute the standard deviation of the differences, and then compute these statistics, d bar over sd by under root n. And you will get t value and p value. Degree of freedom will be not differences is the only one variable. So degree of freedom will be n minus 1 because they are present in pairs. So let me give you the practical demo for this one. So here is a practical demo for pair t-test. Pair t-test. So here is pair t-test. All right. Now, this is before giving the treatment score, this is after giving the treatment score. And now you apply this. We are testing mu d is equal to 0. You can write down H naught mu d is equal to 0. That difference between before and after, they are 0. Alternative, they are different from 0. Okay. Analysis, compare means, paired t-test. This is paired t-test. Go to paired t-test, then after score, before score, and simply press OK. If you press OK, you will see there are 20 pairs. Degree of freedom is 19. Obviously, one less than. And this is your t-value, 2.729. And this is p-value. Yes, please. Can you tell me how much is a p-value? Yes, please. Anybody?
0.013.
Which is less than 0.05 or more than?
It is more than 0.05.
0.01 is less than
Oh, less
0.05 or
than.
more than? Yes,
Less
please?
than.
Less than. So 0.05, 0.01
Is less than
3
0.05.
is less than 0.05. If it is less, we have to reject or accept.
Reject the null
Reject
hypothesis.
the null hypothesis.
Reject the hypothesis. What was our hypothesis? Mu d is equal to 0. That means mu d is not 0, the medicine is effective. So our conclusion here is the medicine is effective. Suppose this would have been 213, 0.213. Suppose. Then what was your conclusion?
Null.
Anybody, please?
Null hypothesis would be accepted, sir.
Yeah, null hypothesis would be accepted. That means the medicine is not effective at all. Yes or no?
Yes.
Yeah. So that is, now we have discussed one sample t-test. We have discussed two independent t-test, two sample independent t-test. We have also discussed paired t-test. These tests are applicable. These tests are applicable only when your data comes from, yes, please, only when your data comes from.
Normal distribution.
But suppose data doesn't come from normal distribution. If data doesn't come from normal distribution, then we apply which type of test? Anybody?
Non-parametric.
Non-parametric test.
Non-parametric.
Now, where are the non-parametric tests? I'll give you one or two examples of non-parametric. For example, analysis, there is non-parametric test. Let's say legacy dialog, and again you come to now one sample, because in one sample t-test, there is a substitute of one sample t-test. If data doesn't follow normal distribution, that is called binomial test. So you can apply this binomial test in non-parametric. That is, this test is called basically sign test. And if you have two sample, this is for one sample, right? And if you are having two independent sample problems, like pizza diet and non-PG, or PG or UG group, then this is called two independent sample problem. That is also there. Two independent sample problem in non-parametric. So there are parallel tests. I'll give you a complete table where there are parallel tests. Similarly, whenever there is a paired t-test problem before and after, so that is covered under these two related samples. I can show you. So here, see, in parametric test, means are tested. Mu is equal to something. Mu1 is equal to mu2. Mu d is equal to 0. Every time mu is tested. Yes or no? Hello?
Yes, sir. Yes, sir.
But in case of non-parametric test, means are not tested. Medians are tested.
We can.
So here the problem will be that m is equal to m naught. If m stands for median, so my first one sample problem will be m is equal to m naught. Two sample problem will be m1 is equal to m2. Paired sample problem will be md is equal to 0. So one sample problem is called binomial test, sign test. Two sample problem is called here two independent sample problem. Parallel tests are there. And now this before and after, which I'm going to do now, this is called Wilcoxon test, Wilcoxon matched pair signed rank test. So again, same thing, after, before, but if data doesn't follow normal distribution, then you have to apply this. And you just have to see p-value. What is your test statistics here? In non-parametric, m1 is equal to, you can write down h naught, please, md is equal to 0, where d is small d. MD is equal to 0. Then mean difference in medians is equal to 0. So press OK. And here you will get the result. So this is the p-value which is coming up. Significance, p-value. What is the p-value here? Yes, please. What is the p-value here?
0.024.
And which is less than 0.05 or more than?
Less
Less
than.
than
Less than.
Less than 0.4.
Achha, okay, what was our H0? Our H0 was MD is equal to 0. That means mean difference in before and after is equal to 0. That has been rejected? Yes or no?
Yes, sir.
So that means
Yes, sir.
again you can say medicine is effective. Medicine is effective.
Effective.
So there are parallel tests actually. So there are parallel tests in non-parametric. If your data doesn't follow the normal distribution, apply these tests. You follow my point?
Yes, sir.
Same way in paired t-test, sorry, independent t-test. Let me do it for independent t-test also, because our time is running out. We are left with 10 minutes. Independent t-test. I'll apply non-parametric with the same data. If you are already familiar with, if you remember independent t-test, PG and UG group. Suppose data doesn't follow normal distribution. Now I'll apply non-parametric. So you can write down the hypothesis for this. See, in parametric, what was the hypothesis for this problem? If you remember, mu1 is equal to mu2. Yes, madam.
mu1 is
Yes,
So
sir.
in non-parametric, what will be the hypothesis? M1 is equal to
M2.
M2. That means median of the first group, PG group, is same as the median of the second group, right? So go to analysis again. Go to non-parametric. In non-parametric, go to 2 independent samples. This is 2 independent samples. And take your test variable on this side. Your grouping variable here. It says again define groups 1 and 2. Same thing, exactly same thing. And Mann-Whitney test. So 2 independent is called Mann-Whitney test. Apply this, press OK, and you will get p-value. So this is your p-value. What is the p-value here? 0.00.
One.
Yes, please.
1.
Again,
Again,
hypothesis
reject.
will be rejected. So there is a significant difference between PG and UG.
UG, IQ
So
levels.
hopefully you can understand where to apply non-parametric, where to apply parametric test. Yes or no?
Yes, sir.
Okay.
Yes.
Now we are left with 10 minutes and I'll give you one-way NOVA. How to apply one-way NOVA. Do you want to learn? Yes, please.
Yes, sir.
Yes, sir.
Yes,
sir.
yes.
Okay. So many people are saying yes, sir. That is good. So what is ANOVA? ANOVA is basically extension of t-test. In t-test, we can test only 2 groups, just like PG and UG or convent or government school. Only 2 groups. But suppose there are 3 groups. Let's say there is one population PG, another is UG, third one is metric also. Then I want to compare whether all the 3 they are having the same IQ levels or not. I want to test this. Now I cannot test by using t-test because t-test restricted only to 2. But ANOVA is an extension of t-test. Here you can use more than 2 groups to compare. Suppose I want to compare 3 groups, 4 groups. So analysis of variance is a technique which partition the total variation present in the set of observation into number of components. You have another class at 4:30 or not? Yes, please. Do you have another class at 4:30?
No,
Sir,
it will be
it's
started from 5.
PM.
It will start from 5, right?
Yes.
Yes, sir.
We have a 30 minutes break, sir.
Okay. Then I can take 5 minutes in between or not?
Yes, sir.
Yes, sir.
Yeah.
Okay, I'll explain you. So analysis of variance is a technique which partition the total variation present among the set of observations into number of components. Now you will not be able to understand what I'm saying, but I'll explain you through example. You will be able to understand that what is the meaning of this, that it partitions the total variation into number of components. What is the meaning of this? Let me explain you. So in one-way ANOVA, in t-test, you were testing mu1 is equal to mu2. But suppose there are 3 groups, then ANOVA can be used. Mu1 is equal to mu2 is equal to mu3. If there are k number of groups, you can test mu1 is equal to mu2 is equal to mu3 is equal to mu4. mu k, right up to mu k, right? So let me take up one example. Now, whenever we go to market, let's say I want to buy tubes or bulbs for my home. Then we want to buy that brand which is having the maximum life length or the minimum life length. Yes, please. What do you want to buy? Which brand you want to buy? Which is having the more life length or which is having the less life length? Common sense. Yes, please. More. So you want to buy those tubes which are having more life length, right? So that it can last longer. Suppose there are different brands available. Let's say first brand is reported to Bajaj, second is reported to Sylvania, third one is Philips, fourth one is Crompton, maybe, and something else. And now I test the hypothesis. If I take 4 brands, suppose I take 4 brands, one is Bajaj, Philips, Sylvania, Crompton, and I test this hypothesis that mu1 is equal to mu2 is equal to mu3 is equal to mu4. That is my H0. What does this mean? That means the life length of all the brands is same. You can write down, please. Write down H0. Mu1 is equal to mu2 is equal to mu3 is equal to mu4. What is the meaning? That the life length of all the brands is same. Have you written? Yes, please. Have you written this part?
Yes, sir.
Okay. Alternative also you write down. Alternative is now I cannot put not equal to. Why? Because 2 brands may have the same or they may differ from other. So what we generally write under alternative in ANOVA, at least 2 of them may differ. Please write down the alternative. At least 2 of them may differ. At least 2 of them may differ. So your H0 is mu1 is equal to mu2 is equal to mu3 is equal to mu4. What is alternative? Yes, please. Can you read alternative? Anybody?
At least 2 will differ.
At least 2 of the groups will differ, right? At least 2 of them may differ. That's your alternative. So there may be difference in 2, there may be difference in 3, 4. In all it may be. Okay. Now here is a very common sense problem. Suppose after applying ANOVA, my p-value was coming out to be non-significant, and I accept H0. That mu1 is equal to mu2 is equal to mu3 is equal to mu4. That means the life length of all the brands is same. I accept the hypothesis. If you accept the hypothesis, you are safe. Your experiment is over. Buy any brand because the brands are same. Yes or no? Hello? If you accept the hypothesis. Anybody can answer what I'm saying? That suppose I accept the hypothesis that the life length of all the brands is same. Then the experiment is over. Go to market, buy any brand. Yes or no? Yes, please.
Yes. Yes, sir.
इतना टाइम लगाया आपने सोचने में.
Yeah.
Okay. Now problem comes when you reject H0. When you reject H0, the first question comes to my mind. Obviously, the brands, there is a life length of the brands are different now. If I reject H0, the first question comes, which brand is having the maximum life length? Which is at number 2? Which is at number 3? So answer to this is given by another test which is called post hoc analysis. Which is called? Yes, please. Which is called?
Post hoc analysis.
Post hoc analysis. So if your post hoc tests are applicable only when H0 is rejected. You can write down, please. Post hoc test have to be applied only when H0 is rejected. If H0 is accepted, experiment is over. Go to market, buy any brand. All of them are same. So post hoc test has to be applied. Here it is written last line. Post hoc test. To determine which specific groups differ from each other, we perform post hoc test. We perform post hoc test. Now, here is a very interesting example, then I'll stop. Suppose I have K different brands. Now, I take, let's say, N1 number of tubes of brand number 1. Suppose I take 10 tubes from Philips. That is your N1. And put them on testing. Put them on testing. Let's say first tube burns for 106 hours. So that is my Y11. Here you can see Y11, Y12, Y1N1. That means one is fixed. The first script is fixed. That means they are all referring to brand number 1. And how many tubes? 1, 2, 3, right up to N1. N1 number of tubes from brand number 1. Similarly, look at the notation. Brand number 2. 1, 2, right up to N2. N2 number of tubes from brand number, but this 2 is fixed. That means they are all coming from brand number 2. Similarly, kth brand is fixed. K1, K2, KNK. So I am taking N1 number of tubes from brand number 1, N2 from brand number 2, NK number from brand number K. And how many tubes I have taken in total? Total number of observations will be N1 plus N2 plus NK. Yes or no? Yes, please.
Yes, sir.
Yes.
Right. Okay. Now, here is a very important problem. Your first looks into Philips. I put the first tube on test. Burns for 106 hours. So your Y11 is 106. I took the second tube again from Philips. Put them on test. Now this time it burns for 126 hours. So that is your Y12. This is how the observations are. Hopefully you understand how the observations are. Yes, please. From different brands.
Yes, sir.
Right. Now, do you think even in the first column, all the tubes are put on testing, they are coming from the same brand. Do you think they will all burn for the equal number of hours, or there will be some differences? आप 10
Sir, they
ट्यूब
will be
Philips
different.
आप 10 ट्यूब Philips की लेके आए
There will
हैं.
be some.
There will be some differences, right? Okay. So
Yes, sir.
variation will be present in the data. Variation will be present in the data. So this, what is ANOVA actually?
Yes.
ANOVA is basically the total variation, which is called TV. Total variation is called TV. It is split up into 2 components. Which 2 components? What is one is between the variation, another is within the variation. Between the variation is called BW. Within the variation is called WV. Now, there are variations present in this data. There are 2 types of variations only. Either the variation will be the between the brand variation or within the same brand variation. Yes or no?
Yes.
Yes, sir.
Now,
sir.
what do you think? Between brand variation will be more or within brand variation will be more?
Between brand variations.
Yeah, between brand variation will be more because they are coming from different brands, different materials, different machines, different people are operating. So all these are different. And within you will expect that their variation will be less. Yes or no?
Yes.
But total variation is sum of 2 components. Between variation and within variation. And this is nothing but ANOVA. So now you go through the first line, which I was mentioning. This line. It is a technique which partition the total variation present into the set of observations into number of components. You understand now? Hello? You understand this?
Yes, sir.
Yes, sir.
Okay. So this is what we want to do. Now, what we are testing here, please write down H0 we are testing. mu1 is equal to mu2 is equal to up to mu k. That all the brands are having same life length. Alternative is they are different. I mean, there is different at least in 2. There may be more. All of them may differ or not. Okay. So this is the table, very important table. Now, how many brands we are testing? Yes, please. How many brands we are testing? Brands. Brand number 1, brand number 2, brand number K. How many brands are here? P1,
number.
B2, K number, right? Yes,
Yes,
please.
Yes, sir. Key number
So-
of friends.
So between variation depends upon how many brands you are testing. If you are testing K number, your degrees of freedom for between will be K minus 1. And how many total number of observations are here? Yes, please. Total number of tubes, observations. Yes,
Sir,
please.
NK.
NK is for the kth brand.
12.
Total. It is written here. Total number of observations. How many?
N number of.
N. So for total, the degree of freedom will be n minus
N
1.
minus 1.
For total, the degree of freedom will be n minus 1. For between, the degree of freedom will be k minus 1. Can you compute for this or not? N minus 1 minus k minus 1, because you take this to this side. So degree of freedom for within will be n minus k. अगर तीन में से आपको दो पता है तो तीसरे की वैल्यू निकल सकती है कि नहीं? Yes or no?
Yes, sir.
निकल सकती है ना? Do you follow हिंदी or not? Anybody please?
Yes, sir.
आता है हिंदी? आता है समझ में आपको मैडम?
Yeah.
अच्छा चलिए ठीक है, कोई बात नहीं. Okay. So now you can prepare this type of table. Here it is. It will compute what SPSS will do in applying ANOVA. It will compute sum of squares, between sum of squares, within sum of squares, total sum of squares. This plus this will be total, and degree of freedom for total is n minus 1. Degree of freedom for the between sample is k minus 1, and this minus this will give you n minus k. You will get this type of table. You will not have to see this table to focus on p-value. Now then, mean sum of squares. How it is being computed? Sum of squares due to treatment. Here sum of squares due to brands. So this SST divided by its degrees of freedom, k minus 1, you will get mean. Divide by sum of squares due to error. So this is called mean sum of squares due to error. Divide SSC divided by n minus k. And once you divide these two, MST divided by MSC, you will get F value. So F value is nothing but MST divided. You will not get T value in ANOVA. You will get F value. You will get F value. So F value here, MST divided by MSC, and reject H. You corresponding to this F value, there will be P value, and reject your hypothesis if P value is less than 0.05. So this is the table you are getting. So I'll give you a practical demo in which between sample sum of square will be there, within sample sum of square will be there, total will be there, degree of freedom will be computed, and you will get F value and P value. But you have to apply post hoc test only when H0 is rejected. Otherwise, do not apply. So just give me 2 minutes now. It will be over. So let me take up another example of one-way ANOVA. So this is one-way ANOVA. All right. So one-way ANOVA problem. It's the same problem which I discussed, that I have taken few tubes from Bajaj, then note down their life length, then after that Philips, after that Crompton, after that Sylvania. So 4 different brands: Bajaj, Philips, Crompton, and Sylvania. I have given this as 1, 1, 2, 2, 3, 3, 4, 4, and later on I have given the labels that 1 is Bajaj, 2 is Philips, 3 is Crompton, 4 is Sylvania. This is how I label. So you can write down the hypothesis, please. You can write down the hypothesis. So there are 4 brands. Can anybody tell me what will be hypothesis here, H0? Yes, please. What will be hypothesis?
The lifeline of all the brands will be same.
Yeah. And mathematically, how you can write mu1 is equal to? Mu1 is equal to mu2 is equal to mu3 is equal to
Mu4.
mu4. All right. Alternative you already have. At least 2 of the brands may differ. All right. So let's apply. Please see, it is just a click away. Analysis, compare means one way ANOVA, your dependent variable is your life length, factor is your brands. And then in the post hoc, you also apply post hoc simultaneously. We will see there are different type of post hoc. We generally go for Schaffe or Tukey. Either you can apply Tukey's test or you can apply Schaffe. The advantage is you will get homogeneous grouping also. If some brands are same, it will be put into one group. If they are different, it will go to the another group. If they are still different, they can go to the third group also. So continue. And in options, you must click on to descriptive and means plot. That's all. So press OK and you will get the result. So here the table I was talking about. First of all, it will give you a mean and SD table for each brand. 11 tubes from Bajaj, 9 from Philips, 9 from Crompton, 8 from Sylvania. So total, how many tubes you have taken total? Yes, please. How many total?
37.
37. So what is the degrees of freedom here in total?
36.
36.
How many brands were there? Bajaj, Philips, Crompton, Sylvania. How many brands?
4.
4.
Four
What is the
times.
degrees of freedom for between?
3.
3. 4 minus 1. And there is no need to compute this. 36 minus 3 will be 33. Similarly, this is sum of squares. Sum of squares, between sum of squares, within. Add these two, you will get total. Now, how to get the mean sum of squares? 3694 divided by 3. You will get 1231. 3539 divided by 33. You will get 107. And then further divide these two. 1231 divided by 107. You will get F value. And this is a P value. So P value is how much? Yes, please.
Less than
0.001.
0.000. If it is showing 0.000, you always write down this P value as 0.0001. Please put 1. Please put 1 because P value is never 0. If you are getting 3 zeros, put 1 at the 4th place. Is it clear?
Yes.
Now,
Yes, sir.
Yes,
then,
sir.
now hypothesis will be accepted or rejected? Yes, please.
Will be
Hypothesis will
rejected.
be rejected. So that means there is a significant difference between the
Life length
brands.
of the body.
life length. So that type of test now. Which test? Because
Post-op.
further we want to see
Post-op.
which ones differ, whether one is different, Bajaj is different from Philips or Philips is different from Sylvania. Which test we have to apply?
Post-op.
Post-op.
Post hoc. So here is the post hoc test. So this is how it is being. It will keep the Bajaj first. Bajaj what at number 1. So Bajaj compare with Philips. Bajaj, this is how to read. Bajaj compare with Philips. This is the P value. What is the P value here? 0.948. Is it greater than 0.05 or less than 0.05?
Greater than.
Greater than. What does this mean? That means there is no significant difference between Bajaj and
Philips.
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 But look at the second one, Bajaj and Crompton. What is the P value here?
Less than 0.05.
That means there is a difference between Bajaj and
Crompton.
Crompton.
Crompton. So then Bajaj and Sylvania. What about this P value?
No difference.
No difference.
Yeah.
This is 0.756, more than 0.05.
Yeah.
So there is no. So Bajaj doesn't differ from Philips. Bajaj doesn't differ from Sylvania. But Bajaj differ from
Crompton.
Bajaj differ from
Crompton.
Crompton. Is that okay? Similarly, once a Bajaj is over, it will keep Philips, second brand. So Philips and Bajaj, same P value you will get because either you compare Philips with Bajaj, you will get the same P value. Yes or no? Whether you multiply 3 with 4 or you multiply 4 with 3, you will get 12. So same thing is happening here.
Yes.
So there is a duplication. So similarly, you can read all this. But rather than going for all multiple comparisons, the better way is, because we have applied Shefe, we have got this table, which is called homogeneous subsets. So it has, where there was no significant difference, they were put into one group. Where there was a difference, been put into another group. So it has made two groups, one subset, another subset. If you see, Crompton is in one group, while Sylvania, Bajaj, and Philips, they are in another group. Yes or no? Yes, please. Hello?
Yes.
Yes, sir.
Right? Now, if you see, this is the life length, mean life length of Philips. This is of Bajaj. This is of Sylvania. Which one is having better life length? This is 84, this is 82, this is 76. Which one?
Philips.
Philips. So that means Philips is having better life length. But we have seen that there is hardly any difference between Bajaj and Philips. So let's say when you go to market, the Philips of Bajaj is 30 rupees costlier. No, sorry, Philips is 30 rupees costlier than Bajaj. Now, which one you will buy then? You will go for Bajaj maybe, because there was hardly any difference between the life length. Yes or no?
Yes.
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 So you can take such type of decision. So it says that Crompton is already out because Crompton is having the less life length, 59 only. So comparison is between these three, and they do not differ much, right? If they do not differ much, then if Bajaj is very if Philips is very costly, you can go for Bajaj. जैसे मैं एग्जांपल देता हूं कि कई बार हम लोग कोई चीज लेने जाते हैं ना, सो एक चीज बहुत महंगी होती है पर वो पसंद आती है, लेकिन दूसरी को हम लेके आते हैं क्योंकि वो घर तक आ सकती है, क्योंकि सस्ती है। तो ये लेडीज जब सूट लेने जाती हैं, दो तरह के सूट होते हैं। एक तो वो जो पसंद आता है, दूसरा जो घर पे आता है, क्योंकि कई बार पसंद वाला महंगा होता है, वो घर पे नहीं आता, उससे सेकंड नंबर का आता है, बट देयर वाज हार्डली एनी डिफरेंस, तो आप सेकंड नंबर को चूज कर लेते हैं। सेम थिंग इज हैपनिंग हियर, सो यू कैन टेक ए डिसीजन टू बाय बजाज बिकॉज देयर वाज नॉट मच डिफरेंस। दिस इज कॉल्ड वन वे नोवा, और ये इसका ग्राफिकल है कि इसमें और इसमें डिफरेंस नहीं है, बजाज और सिल्वानिया, लेकिन क्रॉम्पटन इज वेरी लो, so you can show graphically also. So this completes your I think the syllabus which have been assigned. And lastly, I'll show you one table where you can see a comparison of one way this parametric and non-parametric. You see, this is parametric test, this is non-parametric test. One sample t-test, there it is binomial test. Two sample t-test, Mann-Whitney test. Paired t-test, Wilcoxon signed rank test. One way ANOVA, Kruskal-Wallis test. So all these are equivalent tests, they are given in non-parametric. Hello?
Yes, yes, sir.
Yes,
So
sir.
if you have any question, please, most welcome to ask. Any question.
Sir,